Hello, we're back. We're looking at one more idea in our limits section, specifically continuity, which we have talked about before. You know the idea of, we're just going to give it a little bit more today. So we're going to start by talking about continuity at a point, both interior and exterior. I'm going to start by drawing a picture. Let's say I have a function that looks like this, where this is some A, this is some B point, and this is C. That means this is f of A. This is a function f of x, we'll name it. That means that this y value we would call f of B, excuse me. And let's even add more. Let's add a point up here. So technically, this y value up here is f of C. So we've got this beautiful drawing. I'm actually going to delete these little dashed lines for a second to make it a little cleaner. Okay, I took out those dashed lines. They were just kind of help us remember what f of A, f of B, f of C is, the y values. So let's talk about continuity at a point. I'm going to first give you the definition, and then we're going to see if we can identify which point this would be. So in order to be continuous at a point, specifically we're going to talk interior point first. So continuity at an interior point. Interior, I keep saying that. You probably know what it means, but on the inside. We'll come back to that in a second. Anyway, in order for a function to be continuous at an, we'll say, interior point, let's say x equals b. Then, all right, we're looking at this point right here, b. As clear, hopefully, it is continuous, right? There's no breaks around b. Well, what does that mean, really? It means two things. The limit as x approaches b of this function is actually equal to f of b itself. All right, so let's look at that. The limit, what my y is getting close to as my x gets close to b, is this y value right here. And there is actually a point there. It's specifically the same thing. Because the limit is equal to the point, it is known to be continuous. Let me show you what it would mean or look like to not be continuous at an interior point. I'm going to draw a couple little pictures, and I'm actually going to take away the orange and the purple here. I'm going to keep this, make sure it's all together, and make it smaller. So we all see, hopefully, right now, that B is continuous at that point, at an interior point. Let me draw two quick pictures to show you what it wouldn't look like. Let's say I have a function that looks like this. And this is B, and the function is here, and B is up here. Here, the limit as x approaches B of this function, it exists. It's whatever this y value is. Maybe I can make this more specific. I'm going to go back a little bit. I greatly apologize. I'm so sorry, ladies. I'm going to make this more specific. Let's say my drawing looks like this. And I'm going to label my x-axis 1, 2, 3. I'm going to label my y-axis 1, 2, 3. So the limit as x approaches 3 of this function is, well, what's my y value approaching here? It's actually approaching, I'm going to say, about probably 1.5. But f of 3, the actual point is up here. F of 3 in this case is 3. 1.5 is not the same as 3. They are not equal, so this is not continuous at an interior point. Hopefully that's not surprising. It is a drawing of a hole. That's one possible example. This could also be true even if there wasn't another point. Basically, if I drew the same picture, but I didn't add a point anywhere, this is another not continuous at, we'll say this is B. Just another drawing. It's pretty much the same thing I drew above. It just doesn't have that additional point. Now, we started with interior point, but I also said we're going to talk about exterior, or otherwise known as endpoints. So if we look at our drawing above, we have two endpoints. Specifically, the points that are on the end. A is our left endpoint, and C is our right endpoint. And in order for a endpoint to be considered continuous, so now this is endpoint continuity, what do you think has to happen? If we look at our 2 points, if we look at the left endpoint and the right endpoint, ask yourself, which of these, which do you think is continuous? Consider for a second. Pause the video if you want. If you said that the left endpoint is continuous, you're correct. If you said that the right endpoint is not continuous, you are correct. Why? Well, the left endpoint, A, actually has a point here. C does not. So now let's talk about what that means in words. In order for a left endpoint to be continuous, I'm going to drag this picture down just so we have it. In order for an endpoint on the left to be continuous, the limit as x approaches that value A from the positive side of this function must be equal to f of A. If we look at our drawing, as I approach A from the positive side, it is the same as A itself. So this left endpoint in my picture, A, is known as continuous. I realize that it does not extend past that, but that's why it's called an endpoint continuity. It's somewhere that it's stopping. So our right endpoint continuity, hopefully you can maybe make an educated guess. If the limit as x approaches, let's say some value c from the left side this time, of that function is equal to f of c, then it would be continuous. But if we look at it in our picture, this is not true. In our image, c is not a continuous endpoint. Why? Because this limit over here, as I approach from the left, is not the same as the actual point itself. There is a hole at c. It is not a continuous endpoint. All right, let's talk about more continuity. Specifically, what does it mean to be a continuous function? This is an interesting idea. So I'm going to first give you again the definition, then I'll draw a picture. A continuous function is one that is continuous, on every value in its domain. I'm going to give you an alert. This alert is that, guess what? I'm going back on something we said earlier this year. This is actually an idea that I'm still kind of learning myself. Let's consider our function f of x is equal to 1 over x. Hopefully in your mind, you are imagining our rational function, this 1 over x graph. Hopefully this is what you're seeing. And let's think about the domain. Our domain can be everything except 0. X cannot be equal to 0, right? If I divide by 0, I'm going to have an issue. That's why I have this asymptote right here. And we have an asymptote right here, but that's not really the important one in this case. Now here's the interesting thing. This function is known as a continuous function. Why? Because x is not a part of its domain. Excuse me, 0. 0 is not in the domain. So if I look at this left side, all the negative values, is this curve continuous? Yes. If I look at the right side, all these positive values, is that piece continuous? Yes. There is this asymptote at x equals 0, but because it's not in the domain, it's actually considered a continuous function with a discontinuity. Strange idea, I realize it. You might be thinking, well, what the heck? This is really weird. It is. Calculus ideas are a little weird, but it's also kind of cool. Let me give you one other example of a function that we kind of know, maybe don't know as well. What about our f of x is equal to the greatest integer function? Remember, what did this look like? Well, this was our step function. Kind of looked like this. The domain here is all real numbers, from negative infinity to positive infinity. I can plug any value into this, but here's the issue. What do we get out? We only get out integers. So this is an example of a function that is not a continuous function. I'm going to scroll down a little. This is an example of a non-continuous function because there are values in the domain that have issues, right? We have all these jumps here that are not a continuous function on its domain because we have all of these jumps. I'm going to have you do one really quick example, and then that's it for today. Here's my image. The question is, on what intervals is the function above continuous? Because they ask us for intervals, get your answer in interval notation. Pause the video right now, consider this problem, and then unpause to find the answer. Here's our solution. All of the intervals where this function is continuous. Notice we have brackets and parentheses. Brackets would mean equal to, parentheses mean not equal to. All right, that's it for today. Look online for the worksheet and the assigned problems.